For a very long time, people had confident explanations for these. They were tongues turned to stone, and they protected you from poison. They turn up in rock all over the world, broad, heavy, triangular, serrated along both edges, and far too big to belong to anything anyone had seen in the sea. The earliest written account we have is from Pliny the Elder in a volume of his Natural History from the year 73. He described them as resembling petrified human tongues and recorded a Roman folk belief that they fell from the sky during lunar eclipses. They were called glossopetrae, tongue stones. On Malta, a 12th century tradition held that they were the tongues of serpents, turned to stone by Paul the Apostle when he was shipwrecked there and given the power to neutralize venom. That belief had consequences. From the 13th to the 16th century, tungstones spread through Europe with ever grander claims attached, antidotes to a widening range of poisons. Medieval and Renaissance nobility mounted them as protective amulets and set them into tableware so that a poisoned cup would betray itself when the stone touched the liquid. By the 16th century, people were consuming them directly, ground up as an ingredient in a manufactured medicinal stone. And this is not only a European story. In the Americas, these teeth were valued long before any of that. Pre-Columbian cultures modified them into projectile points, knives, jewelry, and funeral goods. Some societies in Panama seem to have used them mainly for ceremony. And there was a trade. Algonquian peoples were mining these teeth around Chesapeake Bay and trading them selectively with the Adena culture in Ohio as early as 430 years before the Common Era. So before this animal was a scientific object, it was a commodity, a talisman, a tool, and a grave good for well over 2,000 years. Which raises the question this episode is really about. Everything we say about this animal is inferred from objects like this one. So how much can a tooth actually tell you? Some people had suspected the truth for a long time. In 1554, the cosmographer André Thevet reported the idea that they were shark teeth as hearsay, and he did not believe it. The first real scientific argument came in 1616 from the Italian naturalist Fabio Colonna, who published an illustration of a Maltese tungstone beside the tooth of a great white shark, and pointed out that they were obviously the same thing. Colonna went further and did an experiment. He burned samples, observed carbon residue, and argued that proved an organic origin. It was good reasoning, and it did not convince people. The sticking point was geography. If these are shark teeth, why are they found far inland in the middle of continents in solid rock? The argument was taken up again late in the 17th century by Robert Hooke, John Ray, and the Danish naturalist Niels Steensen, better known by the Latin form of his name Nicholas Steno. In 1666, a great white shark was caught and its head brought to Steno to dissect. His report the following year set the teeth of the shark beside the tongue stones and settled the matter for anyone paying attention. There is a lovely piece of scholarly untidiness here. The famous engravings in Steno's report, the shark's head and the fossil teeth, are not his. Neither image shows the animal he dissected. Both had been commissioned in the 1590s by a papal physician, Michel Mercati, for a book that went unpublished when he died. Steno reused them on a colleague's advice that a picture of the actual dissected head would be unsuitable for readers. But Steno's real contribution was not the picture. It was answering the inland problem, and in answering it, more or less inventing a science. He observed that the rock layers containing these teeth also contain marine sediments, and reasoned that those layers had been laid down underwater, then covered and lifted by geological activity. That is the principle the whole of this series rests on. Rock layers are a sequence. They record the environment they formed in, and the ground can move. The animal got its scientific name from the Swiss naturalist Louis Agassiz in his enormous study of fossil fishes published through the 1830s and 40s. He called it Megalodon, from the Greek for big tooth, first in an illustration in 1835, then formally, and revised the genus because the teeth were far too large for the one he first chose. Today it is classified as Otodus megalodon in the extinct family Otodontidae. And that reclassification is the first place the popular story goes wrong. For a long time, Megalodon was placed in the same family as the great white shark, on the strength of the teeth. Big triangular serrated tooth, obviously relatives. Most researchers now think that similarity is convergent evolution, two lineages independently arriving at the same solution because they were doing the same job. Look closely and the teeth differ. Megalodon's serrations are much finer than a great white's, and the great white turns out to be more closely related to the extinct broad-toothed mako and to the living mako sharks. The two lineages diverge on this reading back in the Early Cretaceous while dinosaurs were still walking around. They are distant cousins that happen to converge on the same shape. Its actual lineage is a chain of increasingly formidable sharks. Auriculatus, Angostidense, Chubutensis, Megalodon, and you can watch the teeth change along it. The serrations increase, the crown widens, the shape becomes more triangular. and the little side cusps at the base of the tooth gradually disappear over a process taking roughly 12 million years. That is not decoration, it is a record of changing tactics, from a tearing, grasping bite suited to fish to a cutting bite suited to something much larger. The teeth changed because the prey changed, and the prey became whales. Now, the hard limit on everything we know: sharks are cartilaginous. Cartilage does not fossilize the way bone does. There is no Megalodon skeleton in any museum on Earth. What we have is teeth, millions of them, because a shark sheds and replaces teeth all its life, some vertebrae, and, since 2023, a set of placoid scales. Those scales are 3/10 to 8/10 of a millimeter across, with widely spaced keels. Tiny and unexpectedly informative, we will come back to them. Everything else, the size, the shape, the speed, the behavior, is inference from those fragments, plus comparison with living sharks. Which is why the numbers keep moving. So, it is worth understanding what a shark tooth actually is, because this whole animal is reconstructed from one. A shark's jaw is not a set of fixed teeth. It is a production line. Rows of teeth run along the line of the jaw, and behind each functional tooth sits a series of replacements, waiting. Most sharks carry about 5 series, with roughly 15 rows in each jaw. A bull shark can have 50 rows in 7 series. Only the outermost is doing any work. A tooth is only shed once the new one behind it has formed and pushed it out of the connective tissue holding it in place. Nothing is ever left as a gap. Sharks lose at least one tooth a week. Because of the way the rows and series are arranged, a lost tooth can be replaced within a day. Young sharks can replace teeth weekly. Over a lifetime that adds up, some sharks shed something like 35,000 teeth, which is why the fossil record of sharks is essentially a fossil record of teeth. Teeth are made of resistant calcium phosphate. The cartilage skeleton is not, and it goes. The oldest shark-like fish date back about 450 million years to the late Ordovician, and they are known almost entirely from fossil teeth and skin denticles. Even the replacement rate leaves a trace. In living sharks, warmer water speeds tooth replacement up, and colder water slows it down. And the teeth themselves are not one thing. There are 4 broad kinds, and each is a statement about diet. Dense, flattened teeth for crushing shellfish, nurse sharks, angel sharks, animals working the seafloor. Long, needle-like teeth for gripping slippery fish, blue sharks, bull sharks. That was the first common style, present in the Devonian 400 million years ago. Pointed lower teeth for gripping, combined with serrated triangular upper teeth for cutting, the great white's arrangement for cutting large prey into pieces small enough to swallow. And teeth that are tiny and non-functional altogether, the basking shark and the whale shark, which strain plankton and never bite anything. Megalodon's teeth are the largest of any shark, extinct or living. The smallest are about 1.2 centimeters tall. The largest exceeds 17 centimeters. Now here is the complication that runs straight into the size debate. Tooth shape changes with age. Juvenile teeth start out narrower and more robust. Adult teeth are broader and thinner. And with sex. In many sharks, females have larger teeth because females are, on average, larger animals. There is a name for it, sexual heterodonty. So, a tooth in a drawer is not simply a megalodon. It is a particular tooth, from a particular position in the jaw, of an animal of a particular age, and possibly a particular sex, and all 3 of those change what the measurement means. There is also a market, and it distorts the record. Megalodon teeth are among the most sought-after fossils in the world. The largest can fetch thousands of dollars. Near New Caledonia, fishing and commercial vessels used to dredge the seafloor for them until the practice was banned. In some places, the teeth are so ordinary that they are civic furniture. The phosphate pits of Bone Valley in Polk County, Florida, yield teeth 3 to 10 million years old. In 1976, the state of Georgia made shark teeth its official state fossil because people keep finding them. And one last quiet detail about how they survive it all. A shark tooth takes about 10,000 years to fossilize. The reason fossil teeth are dark, rather than white, is that the sediment burying them keeps oxygen and bacteria away from the tooth. The thing that destroys a tooth is being left in the open. Everything we know about this animal exists because a few of its teeth were buried fast enough. The honest answer to how big was Megalodon is a range, and a wide one. Published maximum total length estimates run from about 14 meters to 24. That is the difference between a very large whale shark and something half as long again. It is not a small uncertainty, and it comes from the method. You estimate from a tooth by measuring it, comparing it against the teeth of great whites of known length, and scaling. That works, as long as Megalodon was shaped like a great white. A 2015 study took 544 teeth spanning the whole geological and geographic range of the animal, from juveniles to adults, and put the most common total length at about 10.5 meters. 10.5 meters is a typical animal. A large great white is around 6, so the ordinary Megalodon was already comfortably larger than the largest predatory shark alive today. The extremes are what get argued about. And in the last few years, the argument has been about the shape of the body, not the length of the tooth. In 2020, a reconstruction based on the proportions of living lamnid sharks gave a 16-meter Megalodon, a head 4.5 meters long, a dorsal fin taller than a person, and a tail fin nearly 4 meters high. 2 years later, the same team produced a three-dimensional model and got a body mass of about 61 tons for that 16-meter animal, well above earlier estimates. Then, in 2024 and 2025, the picture changed again. Comparing the proportions of the brain case and tail against a wide range of sharks suggested Megalodon had a more elongated body than anyone had assumed. A longer, slimmer animal is longer overall and lighter than a stocky one, so the same fossil now yields a length of about 16.5 meters and a mass roughly half the previous estimate. A specimen doing most of that work is a vertebral column from Belgium, about 11 meters of it, from an individual estimated to have been about 46 years old. 46 years old and mid-sized. Not a record animal, a middle-aged one. So, when you see a confident number for the biggest Megalodon that ever lived, treat it the way the specialists do, as a model output that depends on an assumption about body shape which is currently being revised. What we can say with more confidence is what it did, because teeth record function and bite marks record events. The bite force estimated from its jaws runs to between about 108,000 and 182,000 newtons, figures well beyond any living animal. Its teeth were thick and robust, built for grabbing prey and breaking bone. That is a different tool from a great white's, which is optimized for slicing flesh. And the strategy seems to have been different too. A great white typically attacks from below into the soft underside. Megalodon appears to have gone through the chest, breaking the ribcage to reach the heart and lungs. That is a strategy for killing something too large to disable any other way, and it fits an animal whose prey included whales, seals, and sea turtles. Young Megalodon did not do that. Juveniles lived in warm, shallow coastal waters, eating fish and small whales, nurseries, in the ordinary biological sense, and they matter enormously for what happens later. Now the scales. Placoid scales govern how water flows over a shark's skin, and their spacing correlates with cruising speed in living sharks. Measured against that relationship, Megalodon's scales are consistent with an animal that was regionally warm-blooded, but generally not a fast swimmer, capable of bursts to catch prey, but cruising slowly. Regional endothermy, keeping parts of the body warmer than the surrounding water, is a real advantage for a big predator. It is also expensive, and it may be part of why this animal got so large. A 16-meter individual would have needed something like 98,000 kilocalories a day, 20 times what an adult great white requires. That is a whale every few weeks, forever. There is one more hypothesis for the size, and it is grim. In some sharks, the larger embryos eat their smaller siblings in the womb, so each pup is born enormous, which requires the mother to be more enormous still. If Megalodon did that, gigantism feeds itself. Bigger pups need bigger mothers need more food, and the males have to keep pace to breed at all. Megalodon lived from roughly 23 million years ago until about 3.5 million years ago, the early Miocene to the early Pliocene. That end date has itself moved. It was long put at about 2.6 million years ago. A 2019 assessment pushed it back to around 3.6 million. Claims of teeth younger than 2.5 million years are considered unreliable. Which matters, because this is where the internet's favorite idea lives. There is no evidence of Megalodon in the deep sea. It was a warm water, coastal, surface, and shelf animal. Its nurseries were shallow. Its prey was near the surface. Nothing about it suggests an abyssal refuge. And its teeth are the most abundant vertebrate fossil in many marine deposits. An animal that sheds thousands of teeth in a lifetime does not stop leaving them behind because it moved deeper. So why did it go? The likeliest answer is not one thing, and each part of it is a knock-on from the world cooling into the ice ages. First, temperature. This was a warm water animal, and the oceans got colder. The band of water suitable for it contracted toward the equator. Second, sea level. As ice formed, sea level fell, and the shallow, warm coastal shelves where the juveniles lived were drained away. Lose the nurseries, and you lose the next generation, regardless of how formidable the adults are. Third, the food moved. Baleen whale diversity fell, and their distribution shifted toward the poles, into exactly the cold water Megalodon was least suited to follow them into. And there was competition. Whale-eating sperm whales such as Leviathan hunted the same prey, and smaller ancestral killer whales may have too, though that last part is genuinely uncertain, since some early orchinus were probably eating fish and squid rather than large mammals. There is one more detail that reads almost like an epitaph. Megalodon's extinction coincides with a trend toward gigantism in the baleen whales. Whether the whales got big because the shark disappeared, or the shark disappeared partly because the whales got too big, is not a question the fossil record answers cleanly. But the two things happen together. What is certain is the shape of the story. An animal known almost entirely from its teeth, which people wore as protection against poison for 2,000 years, which turned out not to be a giant great white at all, and whose size is still being revised. It was probably the largest macropredatory shark that has ever lived. It grew slowly, ran warm, ate whales through the ribs, and raised its young in shallow, warm water that the Ice Age took away. And when you next see a confident number attached to it, remember what that number is made of: a tooth, a comparison with a living cousin that turns out not to be a cousin, and a model of a body nobody has ever seen.